Students, this lesson is about Riemann sums and an introduction to definite integrals. So I first of all want to talk to you about a Riemann sum, and basically these sums use left endpoints, right endpoints, and midpoints for rectangles or trapezoids, and the difference with a Riemann sum compared to what we've been working on is that the widths of these shapes, either rectangles or trapezoids, do not have to be equal to each other. So as we were doing our calculations in our previous lessons, we had a delta x that was always the same for each rectangle in our calculation, or for each trapezoid in our calculations. But Riemann discovered that those widths did not have to be equal. So in doing that, he opened up the opportunity to calculate what is called a definite integral. And so you'll see the notation for a definite integral is the integration symbol, but you have what we call limits of integration at the bottom and at the top. And so we would read this as the integral from A to B. And that would be your lower limit of integration would be the A, the upper limit of integration would be the B. And then you'll find that definition is related to the limit as the widths of these shapes, either a rectangle or a trapezoid, as those widths would tend to 0, and you do your summation. That would be the same as the number of rectangles or trapezoids becoming infinitely many numbers of rectangles, that those areas would be the actual value of this definite integral. And this definite integral then gives us the area under a curve. So for today, we are going to be working on solving or evaluating, I should say, the definite integral using geometric formulas. And then in the coming days, we will learn what is known as the fundamental theorem of calculus to evaluate all definite integrals. So we're going to take a look at some properties of definite integrals, and then some examples of some Riemann sums, and then other calculations doing geometric formulas. So the first part of this, I will go through our definite integral properties. And the first one is, if you're integrating from A to A, hopefully that would make sense to you that there's actually no area being calculated. And so that would be 0. So if your upper and lower limits of integration are the same, then you have the value of 0. All right, if you are integrating from A to B of f of x dx, that would be equal to the negative of the integral from B to A of f of x dx. For number 3, if you have a number between the upper and lower limits of integration, then you can split up your integration as such. We could go from A to C of f of x dx, and then continue on from there, integrating from C to B of f of x dx. And that would give us our integral from A to B as long as C is in between the A and the B. And then numbers 4 and 5, those are properties that you've seen with the indefinite integral, that if you have a constant, you may take the constant outside of the integral sign. So k times the integral from a to b of f of x dx. And likewise for number 5, you've seen this before, where you can distribute. So the integral from a to b of f of x dx plus or minus, and then the integral from a to b of of g of x dx. So those are some properties that we will use as we start evaluating definite integrals. So notice that with definite integrals, I'm saying evaluate because you will come up with a numerical answer, and this will represent area under a curve. All right, so our first example, actually examples 1 and 2, are going to be the calculation of an integral using Riemann sums. So you'll notice that the points that I have indicated on our given graph are not evenly spaced. So this is what Riemann discovered, that we would be able to draw rectangles or trapezoids by whatever spacing we have information about, and then adding up those areas. So first of all, we're asked to do a right Riemann sum. We're integrating from -2 to 3. So our A is -2 and our B is 3. And so I'm going to, since I'm doing a right Riemann sum, I'm going to start at the 3 and go all the way across, even with my y value for when x is a 3, all the way across until I reach where I have another defined ordered pair. So I have another defined ordered pair when x is a 0. So the height of my rectangle is determined by my right y value and then going all the way across. So this rectangle, I'm going to call it R2 because my first one will begin up here on the right endpoint, and I'm going to go all the way across until I find an ordered pair X that is defined, and this will be rectangle 1. And a right Riemann sum simply means I'm going to calculate the area of each one of those rectangles. So for rectangle 1, it has a width of 2 and a height of 5. So I'll be taking 2 times 5, and that area is 10. Then I'm going to go to rectangle 2, and for rectangle 2, that one has a width of 3 and a height of 2. So a width of 3 times a height of 2 would give me 6. And so my area, which is defined to be my integral from -2 to +3 of f of x dx, would be the sum of those two rectangle areas, 16. And so that's doing a right Riemann sum. Now, my trapezoid, I will erase what I've done here. My trapezoid sum also goes from -2 to 3. And so I'm going to start at -2, connect my first two known points. I'll have my first trapezoid. My second trapezoid will stop at 3, and that will be my second one. So I have trapezoid 1, trapezoid 2. So for trapezoid 1, I have 1/2 times the sum of the bases. Now, my first base is 2, plus my second base goes to 5, and then my height is 2. And so that would give me 7. My trapezoid 2, I have 1/2 times my first base, which is a 5, plus my second base, and that's this base, and that base is a 2, multiplied by the height of that trapezoid, which actually is 3. And so this is going to give me 7 times 3, which is 21, times 1/2. I'll have 21 halves. And so my integral from -2 to 3 of f of x dx, using the trapezoidal sums with n equaling 2. So in other words, 2 trapezoids would be the sum of 7 and 21 halves. So 7 is 14 halves plus 21 halves, and we would get 35 halves. And that's just a little bit bigger than 16. And you can kind of see that that one is an overestimate. And if you paid attention on my drawing for the right Riemann sum, those were both underestimates of the area under the curve. So that would be an example of doing a Riemann sum, noticing that the widths of those shapes did not all have to be the same. And so that can transfer to calculating or evaluating integrals, where we use a variety of geometric shapes. And so if you'll turn your paper over, that's where we're going to continue.